morning, good evening, everyone. Thanks for being here. My name is Yijing, and I'm excited to share our research on similar data points identification with LLM, a human-in-the-loop strategy using summarization and hidden state insights. So let's start with why identifying similar data points is so important. So think about research engines, recommendation system, data deduplication, and anomaly detection. These all rely on finding similar data points. For example, when you search for something on Google, the search engine needs to find web pages that are similar to your query. Or consider Netflix, which recommends movies based on your reviewing history by finding similar movies that you might like. So the traditional methods often struggle with the sheer volume and complexity of modern data. So our research aims to tackle these challenges using large language models to identify similar data points across different types of datasets. So for the challenges in the modern data analysis, we are living in a digital age where the data is growing exponentially. So the data is not just text, it's structured, unstructured, tabular, or even images. The traditional methods like clustering algorithms and nearest neighbor searches often cannot keep up with this diversity and scale. So for example, the clustering algorithm might work well for small dataset, but become computational expensive and less accurate as the dataset grows. And similarly, the nearest neighbor searches can be slow and inefficient for especially the high dimensional data. So there is a real need for innovative, scalable, and efficient techniques to manage and analyze all this data. And for the large language models, they have shown incredible capabilities in understanding and generating human-like text, but their potential goes beyond just the text. They can handle various data types, making them perfect for our needs. So the examples of LLMs include ChatGPT-3, BERT, and other transformer models. And those models can process the widest amount of information and learn nuanced patterns, making them particularly adept at handling different data types. For example, BERT excels at understanding the context of words in a sentence and making it useful for tasks like sentiment analysis and question answering. So let's talk about our approach. We use a two-step methodology. First, we on the top side of this image, we can see that first we summarize the data using LLMs. This will reduce complexity and highlights the essential information. And for example, if we have a large data set of customer reviews, the LLM can summarize each review into a few key points and making it easier to analyze. And second, we extract hidden state using the LLMs, which is the lower part of this image. So this will give us compact feature-rich representations, and those hidden states capture the underlying patterns and relationships in the data. So the goal is to identify similar data points across diverse data sets efficiently and also effectively. And this is the first step, human-in-the-loop strategy. So we bring in this strategy as the data summarization process. So this means users like domain experts can customize summarization prompts and refine them iteratively. For example, a fraud investigator may be interested in specific patterns of transactions, while a marketing analyst might focus on customer preferences. And this ensures that the generated summaries reflect what's most relevant to the user needs, making the data more specific and relevant. And this iterative process allows those users to refine the inputs based on the preliminary output and fostering a dynamic interaction between the model and the users. After the summarization, we process those summaries through a second advanced LLMs to extract the hidden states. Those extracted hidden states are essentially like vectors. So they can represent the distilled semantic and syntactic essence of the text. And they capture relationships, contact, and nuance that are critical for identifying similarity beyond those superficial comparisons. For example, like two customer reviews might be use different words but express similar sentiments. And the hidden state can capture this similarity. And we also use techniques like cosine similarity for similarity analysis and enabling efficient comparison of data points and deeper insights into data relationships. So here is the high-level illustration of our methodology. We start with data point summarization and followed by hidden state extraction, and finally similarity analysis. And this approach works for various data types, including images and tabular data. And a diagram on this side shows this process. And so this process works for various data types and including the images and also tabular data. And we can see like this diagram highlights the flow from summarization of the hidden state extraction and to the similarity analysis. So if we break down the data into manageable summaries and extracting rich features, then we can efficiently identify those similar data points across those complex and large data sets. And here is our first experiment, which involves the MIT Places 335 dataset, which is a vast collection of images characterized into 335 distinct scene types. And in this experiment, we focus on the kitchen images and floor types to evaluate the LLM's ability to summarize and identify those similar images. And the object is just to test like the model precision in identifying the specific attributes like floor type and uncover nuanced similarity among those scenes. For example, we can think about a question like, can this model distinguish between a modern kitchen with a marble floor and a rustic kitchen with a wooden floor? So this experiment helps us understand the model's capability in handling visual data and extracting meaningful features. And here is the result. In this experiment, we summarize the image profiles using descriptive tags that capture the functionality of the room depicted. For example, we can see those tags on the right side, like the tags like modern design, sanitaryware, and shower. Those highlight the key functional and design elements within the bathroom scenes. And the LLM successfully identified those elements and suggesting a standardized approach to tagging. This is our second experiment using the AML sim dataset. So this provides synthetic but also realistic transactional data simulating typical behavior observed in the money laundering scenarios. And the object is to construct comprehensive customer profiles from the tabular data and generate embedding for similarity extraction. And this approach aims to enhance the anti-money laundering efforts by effectively detecting those suspicious activities. For example, like we expect the model identify the patterns of transaction that are indicative of money laundering, such as those frequent cross-border transfers of the large transaction in different currencies. And this experiment helped us evaluate the model's ability to handle those structured data and extract those meaningful patterns. And in this experiment, we summarize the customer profiles using tags that indicate high-risk behaviors, like high-frequency cross-border transactions and large amount in different currencies. And the LLM can effectively distill those transactional data into descriptive tags that reflect risk factor important to AML detection. However, we also observed instances where the model's assessment criteria led to discrepancies. So this indicates the need for continuous model refinement. For example, the model may flag a legitimate transaction as suspicious if it matches certain patterns. And this also highlights the importance of incorporating domain expertise and refining the model's criteria to improve the accuracy. So for the limitations of the model is like the generalization and interpretability will bring some challenges because the LLM's performance may vary across different domains. And the opaque nature of those models can also influence the user trust and complicate the error diagnosis. And additionally, pre-processing inaccuracies can also influence the overall access of the similarity analysis. And computational demands can also be a concern, which may potentially limit the feasibility for smaller organizations. For example, if we run the large language models on extensive datasets require significant computational resources, so that may not be accessible to everyone. So addressing those limitations is crucial for making our approach more robust and widely applicable. Now looking ahead, several enhancements and directions are possible. Increasing model transparency and expanding dataset diversity can improve the robustness. And also, refining models through fine-tuning and transfer learning may enhance accuracy and efficiency. And integrating multimodal LLMs and human in-loop feedback can further optimize the process. And exploring computationally economical models and leveraging cloud-based infrastructure can mitigate the resource-intensive demands. For example, like developing more interpretable models can help users understand the decision-making process, while expanding the training data can improve the model's generalization across different domains. And additionally, incorporating human feedback can help to refine the model's criteria and improve the efficiency. So in conclusion, our research introduces a two-step approach using LLMs to identify similar data points across diverse datasets and showing promise in capturing nuanced similarity overlooked by the traditional model. And these experiments with image and tabular data demonstrate that the LLM's effectiveness in summarizing complex data and detecting high-risk behavior. And despite the challenges, this work paves the way for leveraging LLMs in data analysis, promoting multimodal learning and advancing AI in analytics. And addressing the limitation and exploring future directions will further enhance the method's potential.